Our third speaker of the morning, Keith Allaun from Powerhouse Energy Group, has spent over 10 years in alternative energy as well as 25 years in Silicon Valley and is pioneering distributed electrical generation from waste and, most importantly, distributed production of high quality, low cost hydrogen. He will now speak on the role of fuel cells.
If my wife were to allow me to have a midlife crisis, this is the car I'd drive. That's an incredible vehicle. And I feel like I'm kind of walking into the dragon's den a little bit here. As we're talking about electrifying vehicles, and the vast majority of the focus has been on battery-powered electric vehicles, we bring a different perspective to the fore here. Our company, Powerhouse Energy Group, is focused on converting waste plastic and end-of-life tires into hydrogen, into road fuel quality hydrogen. We feel like this is a technology whose time has come. The idea of bringing the fuel cell to the market to electrify vehicles and take the exact same electric chassis and the same components of an electric vehicle, but just use a different mechanism by which you're powering that vehicle is something that we're able to do. The key challenges that have faced us with hydrogen in the past have been the relatively high expense and, oddly enough, some significant environmental challenges around hydrogen. But hydrogen is truly the cleanest fuel that we could be using. It's effectively the fuel that is powering the sun, and we're just kind of cutting out the middleman. We're taking that hydrogen, we're extracting it from end-of-life materials here, and almost everywhere in the EU, second-use materials or waste materials are considered renewables. In the UK, a large number of these are not considered renewables. That said, we're going to continue on our path to generate hydrogen and extract the most energy value we possibly can. We've created a process over the last number of years to use our distributed modular gasification. We've created a philosophy that allows us to seed these things in relatively small footprints and deliver this road fuel quality hydrogen in an extremely environmentally conscious way. So steam methane reformation, which accounts for about 95% of all of the hydrogen produced in the world today, generates about 16 tons of CO2 for every ton of hydrogen that one creates. Our process generates a little bit less than 1 ton of CO2 for every ton of hydrogen we create. So effectively, we're a carbon neutral process because when that hydrogen goes into a fuel cell and replaces a fossil fuel, that's a carbon negative use of that fuel. We feel like hydrogen fuel cells are making a significant impact on the market, and we're there to start doing something worthwhile with it. Our distributed modular gasification process, again, is a small footprint, and utilizing 25 tons of plastic or less than 2 truckloads full of plastic a day, we can generate on a half-acre site a ton of hydrogen and enough excess electricity after powering our plant to charge a large number of electric vehicles. Basically, we can create 140,000 driving miles a day through one distributed modular gasification site that's creating both hydrogen and electricity. The challenge, of course, is going to be to have the room for the electric cars to fit while they're slowly charging. The DMG process can be cited. We feel like one of the important things is that we want to bring the solution to where the problem exists. Oftentimes, these large SMR facilities that are creating hydrogen are extremely large. They're located at a port or something of that nature, and they have to distribute the hydrogen. There's not an adequate hydrogen gas infrastructure yet. And it's going to be a 25-year process for the gas grid to be fully upgraded to accept hydrogen throughout. There are a number of places in the UK and a number of places in the EU that are starting to test hydrogen being integrated with the natural gas in the pipeline at about a 10% volume to work on household appliances and things of that nature. But our process allows us to site this at a place where we can use end-of-life plastics, we can use end-of-life tires without those having to be transported around anywhere. They can be brought to our facility, which is conveniently located, and we can have a fueling station at that facility, allowing us to fuel up to 200 cars or 40 trucks on a daily basis. Our perception is that we're going to be looking at an early adoption of industrial transport. If we look at the fastest adopter of fuel cell technology, it seems to be public transport and buses. Recently, the TfL here in London acquired and received 23 hydrogen fuel cell buses. The Metropolitan Police also received 11 hydrogen fuel cell Toyota Mirais that they're going to be integrating into their fleet, but they're on track to order 550 additional Toyota Mirais over the next 2 years. So the focus on fuel cells is growing, and the challenge has been the generation of distributed hydrogen. One of our colleagues in the hydrogen business is a company called ITM, a 100 million pound company that uses electrolysis as its means to generate hydrogen. And that is one mechanism by which one can generate hydrogen. And if you're using purely alternative energy to generate hydrogen through electrolysis, then you effectively have a zero CO2 footprint. We've got a slightly higher CO2 footprint, but we can actually use our excess electricity to run an electrolyzer if we choose to. So again, the perception is that the adoption is going to be really in public transport. There have been over 50 trains ordered in Germany to start running on hydrogen. There are new ferries that have come to the fore now that are running on hydrogen fuel cells. And a number of companies are running forklifts, and there's a project ongoing in the Port of LA to eliminate diesel trucks from the Port of LA. We recently announced an agreement with a company in Romania to focus exclusively on the decarbonization of public transport in Eastern Europe. Someone had mentioned mentioned Dieselgate, and while Dieselgate is behind us, what isn't behind us is that Germany is taking all of its old crappy diesel cars and shipping them east. And so they're ending up in places where the air quality is degrading tremendously. Now the EU is actually taken 4 countries to court to start regulating the air quality and eliminating particulate matter in particular, as well as reducing the CO2 footprint in these cities. So historically, hydrogen has been relatively expensive to buy, predominantly because of the cost of distribution. And so getting hydrogen from one place to another is an extremely costly exercise, simply because it is so that you can transport so little of it concurrently. If you look at one of these trucks running down the road, 40-foot trailer filled with canisters of hydrogen, that 40-foot trailer that weighs something in the neighborhood of 40,000 pounds contains 750 kilograms of hydrogen. So it doesn't even carry it, it's not even carrying a ton of hydrogen for each of those trucks that's going by. So the cost of transport has been a major barrier, hence the idea of bringing electrolyzers and now bringing distributed modular gasification to places where people can use the hydrogen immediately, be that a logistics facility or a transfer station or a council fleet that would allow us to accomplish that. Now, we can generate hydrogen at a cost that is comparable or lower than petrol and diesel. That is a true innovation in this market. The cost of hydrogen, the hydrogen that the Met is going to be paying in the city is going to be £10 plus VAT. Throughout the UK, there are currently 7 stations throughout the UK, and throughout the UK, those stations are selling hydrogen at somewhere between 10 and 12 pounds plus VAT per kilogram, which is a gallon equivalent. So again, we feel like the economic impact of being able to produce hydrogen at a reasonable price and being able to do so profitably separates us and sets us apart and opens the doors. One of the keys to opening the door to the hydrogen economy. People have talked about the hydrogen economy oncoming for quite some time, but it's actually starting to get there. Again, I mentioned the fact that we produce a significantly lower amount of CO2, 1/16 the CO2 of traditional SMR hydrogen production. And you know, I talked about electrolysis, but if we only have 50% of our electrical capacity is alternative energy, that means the other 50% is traditional energy, some portion of which is coal-fired brown power. And if one looks at that, then you realize that they're creating a CO2 footprint. They're just moving it from where their electrolyzer is back to the power plant. And in that case, we're somewhere between 1/3 and 1/5 the amount of CO2 that they're producing utilizing their electrolyzer. So the question arises, you know, actually the question doesn't arise about brown or green energy. I think that green energy, we're moving in that direction as quickly as we can. But what does arise is whether it is going to be fully electric vehicles, whether it's going to be fuel cell electric vehicles, there's going to be some portion of internal combustion vehicles for a period of time, even though countries like the UK and Norway and Germany and some of these countries are talking about outlawing ICEs by 2040. Countries farther to the east, countries farther to the south are not going to be outlawing them anytime soon. So they're going to be part of the mix, and hybrids are going to continue to be part of the mix. The expectation is that by 2040, however, the fuel cell vehicles are going to represent fully 25% of the market. And this is not data that I'm just kind of hoping for. This is based on a survey of over 1,000 automobile executives talking about where the trends are and where they're making investments in powering their vehicles moving forward. So these are the guys that are and gals who are chartered with making significant investments moving forward. So a couple of years ago, with the formation of the Hydrogen Council at Davos, a handful of companies, actually about 12 companies that included Mercedes, BMW, Honda, Toyota, Hyundai, committed 10 billion euros to the building of the hydrogen infrastructure in Europe as a starting point for the hydrogen infrastructure. There's something in the neighborhood of 130 million euros available for this project that I had mentioned, the decarbonization of public transport in Eastern Europe, in EU grants. So if we look at the #1 trend between now and 2025, it's not the continued growth of the electric vehicle market. It's actually the advent of the fuel cell vehicle, because fuel cells have become affordable enough, and more importantly, hydrogen is becoming ubiquitous enough. Hydrogen is, of course, the most ubiquitous resource in the galaxy, #1 molecule in the galaxy. And we utilize a very quickly growing resource to generate that hydrogen, and that resource is, of course, waste. As much recycling as goes on, there's always going to be a bit of end-of-life waste that we're going to be able to gasify, eliminate from incineration. Incinerators are continuing to be built throughout the world, and it is a tremendously inefficient mechanism by which to capture the energy value. Our process allows us to extract 85, 90, 95% of the full energy value of any of the feedstock that comes through our process, and to extract the hydrogen from that, and then generate electricity with the tail gas that's remaining. So if we look at the first one, the ability to recharge at home, I was talking to somebody at a conference last week who was mentioning that they think it's going to be a 20+ year project to upgrade the grid to make it adequately robust enough to handle more than 25 or 30% uptake of electric vehicles. So the ability to recharge at home it's not a possibility in many of the homes here today in the UK. There are zero tailpipe emissions, but there are some challenges. This gentleman mentioned range anxiety. And while that may or may not be an issue, the fact is with a hydrogen fuel cell vehicle, you're operating the vehicle the same way one would with a petrol or diesel vehicle. You're able to pull into a fueling station, fuel your car up in 3 minutes and be on your way. And you've got a 300 to 400 mile range in that hydrogen fuel cell vehicle. You're creating energy on board. So you're ending up with the same environmental benefit of no tailpipe emissions. You're ending up with water mist, effectively, as your output. Again, as I mentioned previously, our ability to generate hydrogen at a cost that is at par with diesel or lower than diesel and petrol is truly a market changer. And the fact that we get paid for the waste feedstock that we receive. So when one is getting rid of waste, if you're not familiar with the waste industry, if you're not familiar with end-of-life products, those are actually, whomever receives those gets paid a fee for that. So we get paid for our fuel coming in, our feedstock coming in, and then we get paid both for the electricity and the hydrogen as we're moving forward. So if we look at the hydrogen infrastructure, you can see that there are, by 2030, over 1,000 hydrogen fueling stations in the UK alone. And in Germany, they're looking at 400 by 2025, many of which are being funded by the Hydrogen Council that I had mentioned previously. The global demand for hydrogen continues to increase. Last year, there were 65,000 fuel cells that were shipped. The vast majority of those were for stationary power as opposed to for fuel cell vehicles. But fuel cells have become smaller, more effective, more efficient, and Toyota has made a commitment to have 40,000 fuel cell vehicles on the road in Japan alone by 2022. So the adoption rate, we're truly at the bottom of the J curve of the adoption rate of fuel cell vehicles. So as a company, Powerhouse Energy Group has been working over the past few years to design this technology literally from first principles. We've gone through the process. We've got a demonstration unit up in Chester, up in Thornton Science Park, former Shell research facility, and the process unequivocally works. Now we're in the process of building our commercial facility. We're in permitting planning for a facility up in the Northwest. We anticipate that facility being operational by the end of 2018. So we're moving very aggressively. The distributed modular gasification system, again, 1/2 acre, small footprint, allows us to create distributed electricity and become profitable from day one, simply on electrical sales. So we can sell that electricity through private wire, we can sell it back to the grid, or we can sell it through a variety of mechanisms. But we're generating electricity in the process. And so we're economically viable literally from day one. As we attach the hydrogen components to our distributed modular gasification system, that then allows us to extract the hydrogen out of the gas that we're creating from this end-of-life plastic and used tires. Again, we're at the bottom of the J curve. We feel like this is the time that we're going to be launching. I think that 2018 is going to be looked at as the year that the fuel cell started to gain traction as a motive mechanism for automotive technology. Powerhouse is focused on the increasing demand for distributed electricity, the increasing demand for distributed hydrogen, and the increasing demand for landfill diversion. So pure hydrogen energy is what we're focused on, and we're traded on the AIM. Again, I think that we're a resource company. We're leveraging this resource of waste. PHE is our AIM ticker. This bottle, can you guess how much plastic is in this bottle? Anyone? Okay, I'm going to tell you. It's about 8.5 grams. This bottle, we can extract enough hydrogen to move a hydrogen fuel cell vehicle nearly 40 meters with this little bottle. So this is a powerful, powerful technology. And there are hundreds of thousands of tons, 300 million tons of virgin plastic is going to be created next year. And we have the opportunity to take the non-recyclable component of that and turn that into hydrogen, which will allow us to motivate our cars. Yes, sir.
Thank you for that. I have 3 very quick questions.
Okay.
First of all, what's the capital cost to produce 1 ton a day? Second question is, do you have a facility up and running now? You have a beta site, but when will your full facility be up and running? Mm-hmm. And third, equally important question, is you produce 1 ton a day of carbon dioxide. What do you do with that?
Well, currently, let's go in reverse order. Currently, we'll be venting that carbon dioxide. And if and when CCS becomes a reality, there are some mechanisms by which we, of course, can capture that carbon dioxide. And if it makes sense to do so, we'll continue to do so. But the reality is that this is a step function. We're part of an ecosystem. And that ecosystem is for the elimination of landfill and the creation of distributed hydrogen. And we can do that in a way that is 16 times more environmentally friendly. So it may not be perfect, but it is 16 times more perfect than what 95% of the rest of the world is doing. We'll be operating by the end of 2018 if I have my way, and if we continue to have a bit of a wind at our back. And our expected CapEx for kind of the nth unit for hydrogen generation and electrical generation. So we will be generating about 1.1 megawatts of exportable electricity and that 1 ton of hydrogen. Our expected CapEx on that is somewhere under 10 million pounds. The reality is that we can double the size of that unit, obviously, without doubling the CapEx. So the cost becomes more efficient. However, we're strong believers in the idea of distributed modular gasification. And each of our systems is effectively built on a skid and will be able to be pre-commissioned at a factory, brought together, and commissioned on site, hopefully within 30 days.
Hi, Tom Kelly from ChargeMaster. I currently drive an EV. I do about 40,000 miles a year, electric miles a year. I charge at home on a zero emission green energy tariff. I charge on the public network with a green energy tariff with renewables. The total cost of ownership of my car is lower than a petrol diesel car. I don't have any problems charging in terms of time. We did some analysis on the Shell figures for 9.99 hydrogen in the UK, 9.99 per kilogram. And we worked out it's about £8,000, 50,000 miles versus about £2,000 in an EV. So at £5 per kilo, it's still twice the price of driving an EV. So I totally get the industrial transport application, but from a consumer passenger vehicle, why would I choose hydrogen?
That's a good question. So I've not looked at the specifics of the cost of charging a consumer EV, small EV at this point. That said, there's horses for courses. The slide that I put up didn't say there are going to be 100% adoption of hydrogen fuel cell vehicles. It says there's going to be 25% of the vehicles are going to be hydrogen fuel cells. So for people who are living rurally, for instance, it might be far more convenient for them to use a hydrogen fuel cell than to have all of the infrastructure rebuilt to bring electricity to their house to allow them to charge their vehicle overnight. And so there will be a number of circumstances in which a fuel cell vehicle makes more sense for a consumer than does a battery-powered vehicle. And I think that as we start getting 7 or 8 or 9 years down the road and we start looking at some of the end-of-life issues associated with battery-powered vehicles and how one goes about recycling them, that you're going to see even more adoption of hydrogen fuel cells. Also, I think that hydrogen fuel cells and lithium-ion batteries are likely to be integrated at some point. That the idea, and in fact already there are small fuel cells that are effectively in standby mode should someone run out of, should their battery die. They can switch on the fuel cell, charge the battery, and get moving on. So there's going to be a portion of the vehicle market that is going to adopt the fuel cell technology. Again, it's exceptionally easy, it's exceptionally quick, it's similar to what they're doing today, and I think that the cost is going to continue to come down. While I forgot what your cost of what you were saying, your cost of hydrogen. You were talking about
well, I think you quoted £5 per kilo. So we based some figures on about £10 with Shell. We weren't aware of your solution, so we're just comparing that. So
So the fact is we can sell it at £3 and be profitable. So again, and there's some debate about the calculations of the electricity. The way that you're doing things is absolutely spot on in terms of environmental awareness and taking advantage of the least expensive power available to you. But again, I think that there are some places where it's not going to make sense. When you're looking at apartment blocks with 600 people, you're going to be hard pressed to be charging 300 cars a night. Yes, sir.
Andrew Dice with Newspace. Just 2 questions. Are there any waste products from your process, and if so, what they are? And are there any compression losses? So one of the reasons we're slightly skeptical of hydrogen is producing on large scale, you then need to compress the hydrogen into whatever form you're putting it into a vehicle. Do you circumvent that, or is that built into your model?
No, you don't circumvent it. You still need to compress the hydrogen at a level that that is acceptable to the vehicle. So whether that's going to be 450 bar or 750 bar is kind of still debatable. And so there's an energy cost associated with that, but that is built into our model and we're cognizant of that. In terms of residual products, typically if the feedstock that we're accepting has a mineral component to it, then that mineral component is not going to be processed effectively. It's not going to be converted. We're not able to extract the hydrogen from that. And that's going to come out as something like either a vitrified slag or a talc-like material. Additionally, if all of the carbon is not utilized in the process, then we would end up with a little bit of carbon black. But typically, we're looking at somewhere in the neighborhood of 2 to 3% by weight of material that comes through, and oftentimes that's either ash or some other stiffener that's put into the plastic.
I'm sure you've done a lot of work on this. You've talked about storage, you've talked about transportation, but could you say something just about the actual chemical efficiency of this stuff? I don't quite know how you measure it, but how does it generating power from, say, a unit of hydrogen compare with generating power from a battery? What is the fuel efficiency, effectively, of these competing technologies?
So the efficiency, that's a tough one to gauge. The fact is that from a megawatt of electricity, we can generate more driving miles in a battery vehicle than we can from a ton of hydrogen. However, that megawatt of electricity is also generating a higher CO2 footprint than the hydrogen is. The hydrogen is a carbon negative fuel because it's replacing a fossil fuel, and there's no CO2 footprint in the process along the way. If one looks at hydrogen being a kilogram of hydrogen is effectively a gallon equivalent of petrol or diesel. And so that kilogram of hydrogen allows you to drive approximately 60 to 80 miles. And a gallon of diesel in the most efficient cars allow you to drive 60 to 80 miles. I'm not quite sure how to calibrate the use of a battery in that process.
You said that it costs about £5,000 a day to convert the tires and plastics. Then
I whoops, let's see where that slide was, because it's not costing us. We're getting paid £5,000 a day.
Yeah, 25 tons of waste, £5,000 a day, and you said that would do 140,000 miles.
Yes.
So that works out about 3.5p per mile.
Okay.
Which seems a hell of a lot cheaper than just about anything else.
Yes, it does. I hadn't done that calculation, but we get paid £5,000 per day.
Yeah, and there's a big problem with waste plastic at the moment because China have banned it.
Exactly.
So it must be
ecstatic.
Well, I know for a fact there's enormous supply that having to just landfill.
It's finding its way to landfill. It's finding its way into incinerators. And again, I can't emphasize enough that when you're taking this stuff to incinerators, you're not capturing the energy capability of it efficiently. When you're using our process, you're extracting the most efficient use of it along the way. You're generating hydrogen, you're producing hydrogen, and you're generating electricity through the tail gas that's produced.
Which is cheaper for you, waste plastic or waste tires?
Waste plastic. All right, well, thank you all very much for your time today. 40 meters right here.